Hello everyone, welcome to the second video of 10 AP Physics 1 summaries. Today we'll be looking at the dynamics unit and focusing on conceptual review. If at the end of this video you're looking for more resources, please check out my description down below for links on more concept review and application problems. If you want to target your time towards specific content areas, I'll include timestamps in the comments for each topic. Let's get started. So before we really dig into dynamics, we want to make sure that we understand what it even means. Dynamics is the study of the cause of motion, or more precisely, the cause of changes in motion. Conversely to kinematics, our earlier unit, we're no longer just looking at the motion itself, but we're actually looking at the interactions that cause it and affect it. Here are the big ideas for this unit, so let's situate ourselves in dynamics. This is Sir Isaac Newton, one of the most famous physicists of all time. Because of him, we're actually studying what's called Newtonian physics, or classical mechanics. He outlined a lot of the major things that we're going to be studying over the course of this year. Some of the major ones that we want to look at right now are the laws of motion, there are 3 of them, and gravitation. Before we start exploring his contributions, it's important that we understand the underlying ideas, the biggest one being force. As a student, forces are often presented as this weird, mysterious, ambiguous thing that you know it does exist, but it's hard to explain in words or even to visualize. So forces are, very concretely defined, vector quantities, meaning that they have both magnitude in newtons and direction, and they're required to change motion. So let's say we have this car here and we want it to drive forward. It would require a force in the positive direction right here that would change its motion and accelerate it in the positive direction. So with this vector quantity right here, it would accelerate off the screen. It's important that you understand that forces always come from interactions with other objects. So instead of a force being this strange amorphous entity, you can instead think of it as more of a relationship or an interaction between 2 objects rather than a thing itself. To help us with visualizing forces, we're going to move on to free body diagrams, which I abbreviate as FBDs. This is a lot of text right here, but the essential idea is that if we want to model forces and draw them as the vectors that we know they are, it's important that we can model them in a way that lends itself to algebraic manipulation later for calculations. So let's say we have these 2 people right here, and they're both working on this box. So the box would be an object, and these 2 would be other objects that are having interactions with this object or exerting forces. So if we show this box as a dot right here, or a point mass, we know that it's in vertical equilibrium because its weight force and its normal force are equal. Obviously there's no floor drawn, but you can imagine it. So if we want to show that these 2 are exerting forces, how would we do that? For free body diagrams, what you want to do is you start from the center, which is the object, and you draw forces radiating outwards. I chose this example because both of these objects are exerting forces in the same direction, and perhaps even with the same magnitude as shown here, but they're approaching from different sides. This doesn't matter in a free body diagram because all forces are shown as radiating out from the point mass itself in the direction that it would cause acceleration in. We can extend this idea onto a Cartesian plane right here. This is just another example of if we wanted to show the forces acting on an object, we remove the object from its environment, we no longer have these other 2, and we isolate instead the interactions that it's having, or these vectors. In a free body diagram, our ultimate goal is to find the net force, or the vector sum of these. Let's take a closer look at that. When we're looking for net force, we're basically looking for the total force. I'm sure you could think of many examples of this, not pertaining to physics, like if you gained $5 and lost $3, you would net positive $2. It's basically the same concept. If you can envision a number line, it works basically the same way, where one direction is designated positive and one is designated negative, and you focus on the change based on the direction that you're moving. So if we have this example on the left, let's see what it ends up looking like on the right when we're working with the net force. So let's focus first on the y component. If we have these 2 vectors of approximately equal magnitude and they're both pointing in the same direction, then their magnitudes must sum, and then their net would be in the positive direction. Now if we're working with the pink and yellow vectors, they are obviously pointing in different directions. So what we want to do is subtract the shorter one from the longer one, meaning the pink from the yellow. And because the yellow is larger in magnitude, it's going to have the final direction. So we would get a result like this. When we find the vector sum of these, it is equivalent to this. And that is basically the principle of net force, which is just basic vector addition. It can get a little bit more complicated when you have diagonals and things that are not functioning just on plain old axes, But again, if you just break it into components, the same principles carry through. Let's do some practice. If we have a red vector like this and a blue vector like this, then the sum or the net force must have this same component in the x direction as the blue and the equivalent y component as the red, which would be some diagonal in this direction of magnitude of these were put tip to tail. If we have this example right here where they're of equal magnitude and pointing in the opposite direction, then we get a net force of 0 because their magnitudes cancel out since their directions are opposite and their magnitudes were equal. For our final example, we have red pointing in the positive direction, blue pointing in the right and negative direction. It appears that the vertical component of this blue is approximately equal to the red right here, which means that the verticals should cancel out and we should only be left with the horizontal component of the blue pointing in the right direction. Would you look at that? So with this concept of net force, we can move on to Newton's laws finally. Newton's first law can be presented in sort of a convoluted way. If you have time, I would definitely read. But it is the classic, a body at rest will stay at rest unless acted upon by an outside force. A body in motion will tend to stay in motion unless acted upon by an outside force. It is also called the law of inertia because it essentially defines inertia, an object's natural tendency to maintain its state of motion. On to Newton's second law, we have F equals ma, which is basically acceleration of an object when a net force is exerted on it, is proportional to the net force applied and inversely proportional to the mass it is applied to. This is arguably the most important and most central equation that we'll keep coming back to over the course of the year. If we look at this example right here, we have two things which we can presume are of equal mass, and as we can see from these vector quantities, the length of this one is larger, which designates that it represents a larger force. This has a larger force acting on an equal mass, whereas this has a smaller force acting on an equal mass, so we would expect that this one would have more acceleration, which we can see is true. This brings up an important definition that we'll talk more about later, but I want to clarify that mass is not just a measure of how much stuff is in an object. This was definitely a misconception that I carried into physics. There's actually two ways that we look at mass in physics, one of them being inertial mass and the other one being gravitational mass. And in this unit, we will mostly be working with, you guessed it, inertial mass. We can see in this lovely diagram right here that this crash dummy has inertial mass, which means that when it is experiencing a sudden acceleration or negative acceleration, its inertia will give it a natural tendency to continue to move forward, or a resistance to a change in motion. Newton's third law of motion is often called the action-reaction pair law, because it basically states that when some object A exerts a force on object B, then object B automatically exerts an equal and opposite force on object A. So here are some examples. If we have a man who is pushing against a wall in frustration or whatever emotion he is feeling, when we have a kid being hit by a ball. The first example, we have this man pushing against the wall with this force, and then the wall is exerting an equal and opposite force at the man. Then for the boy, the ball is hitting him with some force in this direction, and therefore the boy is hitting the ball in the other direction with an equal force. It makes sense when you think about the fact that this ball, not only does it hit him, but then immediately after hitting him, it slows down and has a quick negative acceleration because he is exerting a force on it too. If he did not exert a force, then there would be no change in this ball's motion and it would just continue on through him, which obviously does not happen. Let's look at one more example for Newton's third law. Here, if we have a rocket and it is in space and it's moving in this direction and it is letting out fumes and exhaust in this direction. If we look at the forces at work here, we obviously have the force that the rocket exerts on the exhaust and it's moving this way, and then we have the force that the exhaust is actually exerting on the rocket, which is in this direction. These two forces are acting on completely different objects, so it's very important here that you identify that they do not in fact cancel out. Instead, the reaction force of the exhaust on the rocket allows the rocket to move forward like a recoil. Before we finish up this section on dynamics, I want to clarify a few of the common misconceptions that I faced as an AP Physics student. The first one is that objects sometimes exert forces on themselves. The second is that an object at rest has zero forces acting on it. And the third is that velocity indicates the direction of net force. So these are all very close to true, which is why they can be confusing. For the first one, it's important to remember that any force an object experiences is the direct result of another object, whether it be a force at a distance like gravity or a contact force like friction. We treat objects as if they have no internal structure, so we can ignore any internal forces. With regard to the second one, just remember that at rest does not automatically equal zero forces present. Just think of a book sitting on a table. There are forces, like the gravity that the earth pulls down on the book, or the normal force that the table exerts up on the book, but because there is zero net force, there is no acceleration. For the last one, just remember that acceleration is always in the direction of the net force, but velocity may not be. For example, if I'm biking forward and then I'm slowing down, I'm accelerating backwards and my net force is backwards, but my initial velocity is forwards. Okay, we made it! In my next video, we'll move on to gravitation and circular motion. Thank you so much for watching, and be sure to check out the description for more resources and more about me. I'll catch you in the next one for more AP Physics 1 content.